Okay, welcome back to this topic on stereochemistry, namely the conformation analysis of cyclic molecules. Okay. We have seen that the cyclic molecules, the initial concept about its conformation was given by Bayer, and he considered all these cyclic molecules as planar molecules, and based on that he proposed a theory which is called Bayer strain theory. And as per his strain, this is strain means angle strain, and this angle strain is highest for cyclopropane, and then it decreases to cyclobutane, it got decreased. Then cyclopentane almost has very little angle strain, and then cyclohexane as per Bayer's planar theory, that it should again the starts as you increase the number of carbons beyond cyclopentane. If you consider all the cycloalkanes as regular polygon, then the angle strain again starts to increase. Okay. Now, we have seen that this theory became untenable because it was found from heat of combustion data that cyclohexane is the most stable of all these cyclic compounds, amongst all these cyclic compounds, and Bayer strain theory could not explain the stability of cyclohexane and beyond. Okay. Up to cyclopentane, strain theory is perhaps applicable. However, still we have seen in cyclopentane the molecule is not planar. The molecule, although angle strain is very little, but still the molecule prefers to adopt a geometry which is not planar, that is called Packard form. So, it exists in the Packard form. This is the cyclopentane, I am showing it. Yesterday we have discussed this. This cyclopentane exists in two types of conformations. One is called the envelope, another is called the half chair. Okay. In the envelope, 4 carbon atoms, I am showing these 4 carbon atoms are in a plane and 1 carbon is up. So, this is the flap of the envelope. Okay. This is the envelope, this is the flap of the envelope, and this carbon is not very fixed that this is the carbon which has to be up. It just it goes down and then the next carbon goes up. So, becomes the flap of the or tip of the flap of the envelope, and then it actually oscillates between all the carbon atoms. So, you cannot say that this is the only carbon which is occupying the tip of the envelope. It is just fluctuating between all the or oscillating between all the carbon atoms in the cyclopentane. This is the envelope conformation where all the 4 carbon atoms in the plane, and there is another one which is called the half chair conformation. Half chair where 3 carbon atoms are in a plane, these 3 carbon atoms, and 1 carbon is above this plane and another carbon is below the plane. Okay. Now, if in these 2 conformations, again angle strain is very minimal, it has minimal angle strain. So, also in the planar conformation, but it does not adapt planar conformations. A question was discussed yesterday. It does not adapt planar conformation because in the planar conformation there will be what are called eclipsing interactions, or you can say the torsional strain, which is associated because if it is a planar molecule, then all these hydrogens, adjacent hydrogens will eclipse each other, and in order to avoid that torsional strain, the molecule adopts the Packard conformation. So, it is all written here. The energy difference between these two is very little, the magnitude is perhaps not known, it is very little. So, it always oscillates between the two, and moreover as in I said, there is another oscillation going on, that which carbon is up, that is also not fixed. All the carbons can be up one after another. Here also which two carbons are up and down, that is also not fixed. It is always oscillating between adjacent carbon atoms. Okay. So, this is what is called pseudo rotation, this phenomena of conformational flexibility where the carbon is going up and down, that is what is called pseudo rotation. And I said this happens because the torsional strain gets reduced as it adopts the Packard conformation. Then we started the cyclohexane. Okay. Now, in cyclohexane, we have seen that it was Saxe and Moore who gave the first proposed that cyclohexane exists in two extreme conformations. One is called the chair conformation and the other is called the boat conformation. And the name arises because of the geometry. So, it looks like a boat and this looks like a chair. Now, these are the two extremes and amongst these two we will discuss the reasons later on. The chair conformation is more stable than the boat conformation. Okay. And we decided that first we inspect the chair conformation, then we will move on to the boat conformation and we will explain why this is unstable or why this is less stable than the chair conformation. So, for the time being, let us just concentrate on the chair conformation. Now, remember last time what I said, that in the chair conformation, if we number this 1, 2, 3, 4, 5 and 6, these are the carbon numbering of the carbons. So, in this case what happens, there are 3 carbon atoms C1, C3 and C5, they occupy one plane and the other carbon 3 carbon atoms, namely C4, C6 and C2, they occupy another plane. And the middle, these two planes are actually parallel to each other and you can think of an average plane going through the, which is in between these two planes. Okay. And then what we have identified is that there are, because apart from these carbon-carbon bonds, every carbon has 2 other substituents. Okay. Every carbon has 2 other substituents. Now, how to draw these substituents? If the carbon is occupying the top positions, so these are the top positions and these are C2, C6 and C4 occupying the bottom positions. Okay. And at the top carbon, if the carbon happens to be occupying a top position, then the sets of bonds that will be there at the carbon, one will be pointing upwards, vertically upwards, if the chair is drawn in this fashion. So, the C1, C3 and C5 will have 3 bonds which will be vertically upwards and the other bonds at C1, C3 and C5 will be parallel to the next adjacent carbon-carbon bond. So, this is the next adjacent carbon-carbon bond for this carbon and this bond will be parallel to this. And so, while drawing the bond here, so this bond should be parallel to this bond and at C6 you have, this is the way to write the other substituent. Okay. This will be parallel to the next adjacent, I repeat, next adjacent carbon-carbon bond. Okay. So, the but C6 we have not of course identified yet the other bond. What I first said, that consider the top carbons. So, there will be 3 vertical bonds which are pointing upwards and there will be other 3 bonds which will be parallel to the next adjacent carbon-carbon bond. Regarding C2, C4 and C6, because they are occupying the bottom of the chair. So, here they also have vertical bonds, but they will be pointing downwards. So, there will be a bond here, there will be a bond there, a vertical line and there will be a vertical line at C2. So, C2 going down, C4 going down and C6 going down. And the other bonds will be again follow the same rule, they will be parallel to the next adjacent carbon-carbon bond. So, this will be parallel to this, then C6 will be parallel to this one and C2 this will be parallel to this one. Okay. And in the chair another parallel system is there, set of parallel systems, and that is C4, C5 is parallel to C1, C2. We have discussed that yesterday. C1, C6 is parallel to C3, C4 and C2, C3 is parallel to C5, C6. Okay. So, this is the characteristics of the chair form. So, at each carbon there are 2 sets of bonds, 2 sets of substituents, If it is cyclohexane, then these are all hydrogens. Let us concentrate on a particular carbon, say C1, where I could see that because C1 was occupying the top of the chair. So, the vertical bond has gone upwards. This is what is called axial hydrogen, and this is what is called equatorial hydrogen. Axial. So, at each carbon you will have an axial bond and an equatorial bond, or an axial substituent and an equatorial substituent. The definition of the axial substituent is, I told you yesterday, the cyclohexane has a symmetry, has many symmetry elements. If it is plain cyclohexane, so it has got a C3 axis, and it has got a C3 axis because if this is the chair, then if you rotate it, remember this is the head of the chair, this is the leg of the chair. So, if you rotate by 120 degree, so this is the, if you rotate by, again I go back to the original, this is the starting point. So, I rotate along this axis. So, this is the chair that I view now after 60 degree rotation. This is 60 degree rotation because this carbon now occupies the position of the carbon little bit up, but at the same vertical point. Okay. So, this goes there and the chair looks like, now the chair is opposite, the head is up and the leg is down on the right side. So, after 60 degree rotation you come to a chair which appears to be different, where the head and the leg are interchanged. But if you now again give another rotation of 60 degree, then you see, then the head has come back to the right side and the leg has come to the left side. Okay, that means it after every 120 degree rotation it becomes the same. So, that is what is, that means it has got a C3 axis. Okay. So, the C3 axis is right going into the middle and perpendicular to the average plane of the ring. Axial bonds are parallel to this C3 axis. Okay. So, axial bonds, you see all these axial bonds, they are parallel to the C3 axis. So, the definition of axial bonds is not that they are vertical, they are parallel to the axis, the C3 axis that a cyclohexane possesses. Okay. Now, interestingly, when you rotate by 60 degree, the head goes up and the leg just interchanges, head and the leg of the chair interchanges. So, if that be the case, so what I am saying that if you rotate it by 60 degree, then what happens, the chair will look like this. The chair will look like this. So, it is just looking like the mirror image of the earlier one. So, this was the head of the chair on the right side. Now, this is the head of the chair on the left side. This is the leg of the chair in this form on the left side, and this is the leg of the chair on the right side. So, it looks like the mirror image. Now, what was your axis of rotation? The axis of rotation is this. Okay. Now, so that means it does not have a C6 axis because it looks different. Okay. If you give another 60 degree rotation, you get the original one. So, another 60 degree rotation. So, you come to your previous chair from the starting point. Again the head is to the right and the leg is to the left. Okay. So, this is now same as that. So, that what I said. But in addition, I want to point out that after 60 degree rotation, if you now take a, if you place a mirror and take a mirror image, the mirror is placed perpendicular to the axis. So, what will happen? Now, you draw the mirror image of this, the mirror is like placed here. So, now it will look like this. So, this point is here and that point is here. Okay. So, you have to maintain the object distance, image distance. So, now you see the mirror image is now same as the original. So, what I am saying, suppose this is the axis, I rotate it by 60 degree, place a mirror perpendicular to that axis and then get the mirror image, and I see the mirror image is same as the original. So, what does it mean? That means the same axis is also can be called as a S6 axis. So, this if it is cyclohexane, then it possesses a C3, it possesses S6. Okay. So, you can also say that axial bonds are the bonds which are coaxial with either C3 or you can say coaxial with S6 axis. It has got, if it is cyclohexane, it has got a center of symmetry, an inversion point also, because these are the points which match with each other. So, it has got an inversion point and it has got of course, 3 planes of symmetry, and going through these planes of symmetry are going through this and this bifurcating. I can show you in the model. So, this is the chair form. The plane of symmetry can be visualized best if you hold it in this fashion, not like the way we have drawn it in the board. If you hold it, this is the same molecule, and if you bisect now from this C1 and C4, these are 1,4 positions. If you bisect this, you see this is the mirror image of that point, and that becomes the mirror image of this point. So, it has it 3. So, there will be 3 planes of symmetry. One will go through this and that. This, if it is 1, then this is 4. If it is 2, then this is 6. So, it will go C1, C4, C2, C6 and C3. This is 1, 2, 3, 4, 5, 6, C3, C6 and C2, C5. Okay, I can write it here. So, there are planes of symmetry. Again, I have already put it as 1. So, the planes of symmetries are going through C1 and C4 vertically like this, or C3 and C6 or C2 and C5. So, there are 3 planes of symmetry, 3 sigma planes, one I is present and then S6 and C3. So, these are the symmetry elements that are present in the chair form of cyclohexane. Remember, there is no substituent here, because the moment you start putting substituent, these things will get changed also the moment you put substituents. Okay. So, that is, so we have identified this axial equatorial, we know which are how to define them and how to write them also, we know that. Okay. Now, there are as I said, some students find it difficult to write the chair form, and I can give you a very simple way to draw the chair form, and that is that was published in a journal which is called Journal of Chemical Education, a very good journal regarding to aid the teaching of chemistry. And according to that journal, somebody wrote that because students find it difficult to draw a chair correctly, because I have seen students writing chair like all this deformed like this. So, this is not correct. It looks like a chair, but it is a deformed chair. So, so you have to maintain the law of parallelism. That means, this is parallel to this is parallel to that, and this bond is parallel to that. But sometimes you cannot, they cannot write properly. So, how to make it very easy? So, in that Journal of Chemical Education, what they said that you take 4 points at equal distance. Okay. So, 4 points, the distance between them are same, and you take 1 point above the second one and 1 point below the third one, and then you draw it. You join all these, you get a chair. That was in the Journal of Chemical Education, that you draw these 4 lines. However, I modified a little bit. It's better that you modify a little, because here the problem is, I told you that this is also a beta bond, because it is above the plane containing the C1, C3, C5. So, this is a beta bond and this is below that plane. So, that is an alpha bond, because we know we have this alpha beta concept that a reference plane you have to take, and if some bond is above that plane, that is called beta, and if it is below that plane, that is called alpha. So, we have this beta and alpha. If you draw the chair in this fashion, the problem is the beta alpha will be very difficult, because the axial bonds, if you draw that, the equatorial bonds are in some cases what will happen, because this is now in the horizontal direction. So, the equatorial bond here is a problem, because that almost lies in the plane that you are considering. So, it is better that this is not a problem, because this is now going away, this is parallel to this. So, this will not create a problem. The problem is created by these bonds, because they are now placed horizontally. So, the equatorial bonds, now sometimes students get confused whether this is alpha or beta, because it appears that it is lying in the average plane of the system. Okay. So, that is why you modify that mnemonic way of writing a chair. The best way is to you take again the 4 points, but in a little inclined fashion, not in the horizontal fashion, and then put one at the top and one at the bottom, and now you join. And you get the chair. Okay. Then you bypass that problem. Now you do not have that problem. The beta and alpha can be very easily distinguished. Okay. So, it is up to you how to draw the chair, but I have given you a way to bypass. If you face any problem, you can adopt this system of drawing 4 points in a line, but little bit inclined, not in a horizontal fashion, and 1 point at the top, 1 point at the bottom, and then you just join them and you get the perfect chair. Okay. So, that might help, because you are the beginners. So, that might help you in drawing the chair form. So we have identified some of the features of the chair form. Now, another feature of the chair form is that one chair form can, by rotation, what you are saying, that I can interchange the head and the leg of the chair by rotation, by just rotation around the axis. I am not rotating any bond, I am just moving the molecule as a whole. The other way you can change this is like the pseudo rotation I have told in cyclopentane. This also has a pseudo rotation business, that the one which is down, that goes up, and the one which was up, that goes down. So, this is all the time happening in the chair. Not all chairs have this property. If the substitution is there, then sometimes this movement is restricted, but in cyclohexane this is what is happening, that this goes down and that goes up. You get one chair, and the other one is that this goes up and that goes down. Okay. So, basically this is continuously happening, and you see the relationship between these two chair forms, that as you take it up and bring this down, your head of the chair is changed. Earlier the head of the chair was on the left side, now the head of the chair is on the right side. Now, this process is what is called flipping of the chair. So, the chair is flipped, the head becomes leg and the leg becomes head. So, there are two ways to do that. I said one is if you rotate the molecule, you rotate the entire molecule, and in this case you are not rotating the entire molecule, you are actually rotating these along these bonds, you are rotating the system. So, that is half of the operation, and the second operation is you rotate the other two bonds and then you get the mirror image chair. This is what is called flipping of the chair. Okay. Now, in flipping, this is a very important concept, and it is happening in the chair form. As I said, in some chair forms it is restricted. There is a sign to indicate chair this flipping. This is the sign for flipping, equilibrium sign, but then a semicircle on the top of the lines. And then as you flip it, that means you bring this down and you bring this C4 up. So, what you get is a chair form which looks like this. Okay. Up to that point is simple. The next question is what happens to this HAHE. So, first you identify the carbon atoms. The best way is to put the numbers again. Now, C1 was earlier up, now after inversion this is the C1 and this is C2. then C3, C4, C5, C6. Because this clockwise you have numbered it in a clockwise fashion. So, that has to be maintained. So, this 1, 2, 3, 4, 5, 6 that clockwise fashion is maintained. Then the question is that C1, consider the C1 carbon. So, there are two substituents. Interestingly, earlier this was top of the chair. So, the axial bond was up, was vertically upwards. Now, this is the bottom of the chair. So, the axial bond will be now vertically down, and the equatorial bond again follow the same parallel principle, that the equatorial bond will be parallel to the next adjacent carbon-carbon bond. Okay. So, this is parallel to this or this, because they are mutually parallel. So, this what happens? Now, question is, suppose this is I put a star here, okay, and I put a double star on this hydrogen. So, this is a star hydrogen, this is double star hydrogen. Question is, where are these hydrogens now? So, this is the star hydrogen. So, that is now here, and this is the hydrogen which is double star. Okay. The question is, what is the big deal about it? There is a great change that has happened when you have flipped this molecule. The change is that the axial hydrogen now has become equatorial hydrogen, and the equatorial hydrogen has become axial hydrogen. That is the change that has happened. So, axial becomes equatorial, equatorial becomes axial. What about the alpha beta nature of this? This is still beta, because if you take the average plane, if you take the plane of the plane containing C1, C3 and C5, you see that He is still He. Now, this was the star carbon, it is still above that plane. So, this is still beta, and this is still alpha, that is below that reference plane. Okay. So, what are the changes that in flipping, what are the changes that happen or the changes that do not happen? What happens? Axial becomes equatorial, equatorial becomes axial, but beta remains beta and alpha remains alpha. Okay. So, that is what is important. Okay. Now, we started with the chair form, because I told you that for the time being, let us assume that chair form is the more stable of these two, chair and the boat. We have assumed that, but now we have to see what is why this is so. Now, if I again go back to the model for the time being, see what is again go back to what is flipping. In flipping, you take the leg of the chair up and the head of the chair down. Okay. So, when you do this flipping, you have noticed possibly is that if you do the reverse of that earlier stage, that when the flipping was half done, that means I have taken the bottom carbon at the top, then what I end up is what is the boat form. So, it has to go, the flipping process has gone through the boat form. So, you have to involve the boat form during flipping. So, this is the chair, suppose we start with this chair, and then we can show many things with this model. First of all, in flipping what happens? This goes up. Okay. It could be the reverse also, this goes down first, but they do not actually happen at the same time, because there is a problem. If they happen at the same time, so you will go through, at some point you will go through a system where all the 6 carbons are in the plane, and which is not the stable form. The torsional strain will be very high. As I told you that when it is when all the carbons are in a plane, then you see the torsional strain between the adjacent hydrogens. Okay. So, the system will prefer the less energetic pathway, that means less energy involved pathway. So, first take one up and then take the other down. Okay. But you see, while doing so, this is basically done in stages. One goes up, you get what is called the boat form, and then you bring this down, you get the flipped form of the chair. Okay. You see, I told you, I can show you now that what happens to this axial equatorial bonds. This red one is now occupying an axial position and beta pointing upwards. Now, if you do the flipping, concentrate on only on the red that I am showing, this red one. So, when you complete the flipping process, you see now this has become equatorial, but it still remains beta. Okay. So, now what we have learned? We have learned the process of flipping, and we have now involved that when this goes to that form, you have to involve this form, what is called the boat form. Okay. So, now we will inspect that why flipping is just not stopped at this point, why it again that this goes up, that will give this form, the boat form. It could have stopped there, but it does not stop there. This goes down and then get the mirror image chair, or what is the flipped form. So, basically this requires energy, and it does not stop here because this is less stable than the chair form. So, the flipping process does not stop at the boat form, the boat form is occupying a higher energy. So, in the next lecture we will discuss that why there is energy difference between these two, why the chair form is more stable than the boat form. Okay. Thank you.